Okay, great. Today we're going to talk about the second lecture in visualizations. So as always, a quick recap from last week from what we learned was visualizations one, I guess. We learned how to plot qualitative variables, right? And to see this, we've pretty much always used bar plots. Um, uh, so side note, pie charts are heavily looked down upon, and I'll go into a little bit about this later on in this lecture. We also learned about continuous quantitative variables, in which case we have so many options, right? Three of them here in the box plot, the binary plot, and the histogram. And the histogram is by far the most used plot out of these three, at the very least. And of course, the line plot, where yeah, like the x-axis is like, for example, the screen value. We can use a line plot. In this case, it's year. And one thing we also noticed last week was that the code is oftentimes very simple, right? And it always follows this very similar structure. You specify which data frame, you specify the column, the x-axis of the column, and then the y-axis, and then you're done, basically. So today first I'm going to talk about plotting the relationship between two variables, right? And this should come as no surprise to everyone, right? A scatter.
Thank you.
I think I'm using my headphone and microphone, so.
It may be because I was wearing it backwards. Is it better now?
Okay, it's much better now.
Okay.
Thank you.
Okay, so that happens, I guess. Okay, so as I was saying, relationship between two variables. So first is the scatter plot. And as I was saying, with bad audio quality, I apologize. But the scatter plot just shows the relationship between two quantitative variables. And I've assumed you guys have looked at this like pretty much all your life. I assume you guys know what it means. And the many metrics that come with it, for example, the line of best fit, well, I'm sure all of you guys have heard of, or like the associativity, like things like that, right? So to code it, again, it's the exact same structure as per usual, right? So that's you specify the plot. Remember, SS between seaborn, specify the data frame, the X column, the Y column, and the hue just means like these different categories of colors, basically. So if you want to draw the line of best fit, you can call sns.regplot with literally the exact same parameters. Reg just means regression plot, right? So it's like linear regression, which is like sort of the fancy vocabulary. Now, one very common problem that scatter plots have is that you just have way too many data points. So if you remember the baby names data frame, we had like 400,000 rows, right? That's 400,000 points on a graph. This is like maybe like 5 inches, right? 400,000 points on that graph, you're going to be able to tell absolutely nothing on the graph, right? So notice it's very like pretty low amount of data points. And notice how it's already very hard to tell what's going on here, right? See, you've got these points stacked on top of each other. They're like kind of, you don't know how many points here, right? There's like, this could be like 5 or 10 or anything, right? You don't really know exactly, right? And okay, as like a side note, data frames are always so big that this literally always happens. This is probably the most common problem ever when it comes to graphing, right? It's overplotting with scatter plots. Now, the first solution is what's called jittering. Now, as the name suggests, right, you sort of jitter every single one of the dots by like a little bit of noise, a random noise, right? And since the noise is random, right, and it'll affect every point randomly, the general trend of the points will not change, right? And so like if you imagine like if there's like 5 points on top of each other, right, they'd all get random noises and jitter around, and it will look like 5 points, right? So that's sort of like the main idea behind jittering. And how you code it, right, is very simple, because NumPy sort of allows you has like this random function that just allows you to generate random numbers between intervals, right? So in this case, the noise for the x-axis, since it's like -10, like the 10 scale, right? I put an arbitrary bound of -1 and 1. So pretty much this means like give me a number between -1 and 1, and the length of what my series, right? And then I simply just add that noise to create a new x, so an x with a bunch of noise, right? And y noise, I just, since the y-axis is like, you see the scale is a lot bigger, right? So like I want more noise to sort of distinguish it. Right, same line of code, you add it to the y-axis. And again, the exact same line of code, SNSS scale plot. Oh, this S right here just means the size of the dot, right? So if that's like a concern, and you can like specify the size of the dot. So notice how like, I guess, well, I mean, there's still like some overlap here, but it's a lot less overlapping than here, right? So like we can actually tell data points apart in this graph as opposed to here. All right, so that's sort of like the core, or like the first idea, which is called jittering. But okay, so but what if the graph looks like this, right? And again, more often than not, it actually does look like this, right? Where you literally just have so many bullet points or points on the scatter plot that jittering will not help you at all, right? Like who cares if I jitter this dot right here a little bit, right? It's still gonna look like this solid block, solid color, right? Of blue, right? And notice we cannot tell any of these yellow dots. We see we can only see this line here, this regression line. So we know there are yellow dots here, but we can't see at all how many yellow dots there are, right? So, and like I said, no amount of jittering will save this, right? So we obviously need an alternative plan. The first one, and personally my most favorite graph because it looks aesthetically the coolest, is called the hex plot. Now, so instead of plotting one data point, we plot the density of points in that area. And sometimes it doesn't have to be density. I forgot the details, but I mean, you should just assume it's density. So I always think of it as sort of a 2D histogram, where instead of having one-dimensional bins, which are intervals, your bins are hexagons, right? So like this hexagon right here is a bin of x and y values. So where x is like negative, maybe 0 to maybe like -2 or 3 here, right here, and y is between like 41 and 50, right, something like that, right? This like little hexagon, all the points in the hexagon, let's say there's 5 points, then this color will be the color of 5 points, right? So typically the darker the color, the more shaded color means that there's more data points, right? This graph is just the colors are inverted, right? Which means that just basically means the lighter the color, the more data points there are. So if we look at these hexes here, that means that there's the most points, the most concentration of points in these two hexes, right? And if we look back at our previous plot, the slideshow would let me, right? You'll see that this is true, right? Most of our points are in that region. So to plot this, we use something called SNS.joint plot. There's no .hex plot because it's sort of like niche, because the next plot I'm about to introduce is sort of more used than this one, but at least it looks cool. So again, it's literally the exact same parameters, right? Except you have this new parameter, it's called kind equals hex. This joint plots, I will go into a little more detail later on. And that, like FYI, that's like the reason why there's like histograms here, which yeah, I'll talk about a little later. But yeah, so like the idea of the hex plot is instead of getting this like cluttering mess, right, that we saw we get these distributions, right? So we get a sense of where our data majorly lies. One downside of the hex plot is that notice in this plot, for example, I had 2 different colors, right? The hex plot does not support that type of plotting, right? You can't plot like a hue on the hex plot because let's say I have like here, right? So how would I differentiate? Let's say there's like a lot of yellow dots, a lot of blue dots. How would I differentiate that between a place where there's like a lot of blue dots and maybe a little yellow dots, right? So you'd have to like sort of define your color scale like quite extensively. So hexplots have, at least from what I've used, have not been able to plot hues, right? It's like 2 different type of colors, for example, right? Because it's hard to define like what the density means. An alternative is what's called a contour plot. Now, contour plots are similar to topographic maps. Now, I'm not sure if you guys know what topographic maps are. I think it should be topological graphs. Wait, okay, but maybe it's better if I just search an image. Topological graph. Okay, that's not true. Oh, this is the toric. Okay, shoot, sorry. That's not what I meant. But like, so it's where like you have like you're graphing like a 3D plane, right? And you sort of smush like the hills, right? And like make it so that like okay, you know what? I'll just explain like the technical definition. Hopefully it'll make more sense. So it's a contour map is made out of contour lines, right? You see these lines in this graph right here. Each of these lines inside that like circle it encases are points or areas where there's the same density of points, right? And like the hex plot, the darker colors means that there's more data points in that region, right? So in this circle here, there's like maybe a little bit of points, right? So like this circle here, this like outer rim has like a little bit of points. You move into this lighter shade, lighter because I have inverted colors on, but this lighter shade, you move this lighter shade, and there's more points, right? Moving this lighter shade, and you realize that's where the majority of our points are, right? That's like the highest density. Notice these 2 points are captured as well, even though there's only 2 points, right? Like I said, so like this lightest point is where there's the most points. This I think is, yeah, so these are called contours, right? So the idea is that it's very similar to a hex plot, right? You're sort of plotting the exact same thing. If you look at the hex plot, right, you see this like general trend, and you plot this, it's like sort of giving, like you use the same information, right? The advantage is, however, is that we can now split by color. So in this, the egregious example right here, right? If I have the fill equals false, which is I don't fill in the color, right? I just have my contours. I can split the contours by color. And oh, you can't really see it that well here, but these like blues are lighter, right? But since I have inverted colors, that means there's like more data points there, right? And in this case, you see there's a lot more data points here, right? And notice how this graph right here is a lot more interpretable than whatever the heck is going on here, right? Another key point I want to make about contour maps is that you see how these lines are closer together? That means the density is changing more rapidly at those points, right? Because like an area wise, right? So that's like sort of defines like the slope of density changing more rapidly, right? In these parts. If you think of them, you can think of them like sort of like hills, where like the more density, the higher the hill, right? So that's like sort of what's going on. It's sort of like a 3D representation of a map, right? Where you now have this like third variable, which is like density. right? So this is, whenever you plot a scatter plot and it looks something like this, right? This is very unusable. I suggest you go switch to, if jittering gets it done, then great, right? But if that's obviously not enough, then switch to a hex plot or a contour map. And oh, I forgot to mention this, but the obvious disadvantage of the contour map or the hex map or the hex plot is that they generalize information, right? So you lose information about like very specific points, right? So like, for example, this guy lost in the void, right? Because there's only one point, and sadly that's not dense enough, right? Because these densities are way higher, right? So the scatter plot gives you like sort of exact information. The contour plots do not. They give you like rough generalizations, but more often than not, these rough generalizations are a lot better than graphs like this. Right, so those are the main ways you deal with overplotting. And as mentioned before, overplotting is so common that you're probably using a contour plot more often than you use a scatter plot. Okay, maybe that's not true, but it's like you probably use them like around the same. This is what I mentioned a little bit before. It's called a joint plot. So have you ever thought about plotting a scatter or hex or contour or any 2D plot for that matter? Histogram for the y-axis, histogram for the x-axis. You can also plot the KDE of the y and x-axis at the same time, right? Have you ever thought of that? It's like an ad campaign, right? Like, have you? Okay, obviously you never have, right? Because why? But just know at the very least it exists. To interpret this graph, this hex plot, as mentioned before, we have our hex plot in this square. Then this histogram represents our x-axis and densities. And this histogram represents our y-axis, right? So this shows us that the majority of our y value points, right? So the adult literacy rate of females percent is 15. Okay. I'm not gonna pretend. Okay, it's okay. But just to know, the majority of our points are between this like 180% tile, right? And for the x-axis, the majority of our percent is from like here, right? So that's just what like the joint plot just gives you like convenient information. And notice how these like hex plots or contour plots, the shading of it will sort of correspond to these two histograms, right? So like where the x and the y are tallest, you'll see that that's where the most points are. And just to reiterate over and over again, the code is always very simple when it comes to graphing. Pandas and Seaborn and Matplotlib, they always make it very easy, very convenient to do things, right? So you want to do a joint plot, you just specify the data, specify the x column, the y column, and what type of plot. And the kind just means what type of plot you want in this 2D area, right? So it could be like scatter or contour, right? In our cases. The last map I want to talk about is called the heat map. Now, what the heat map is that the x-axis are filled with all the columns in your table, and the y-axis is also filled with all the columns of your table. Now, what each block represents is the correlation coefficient between the two columns, right? Actually, it doesn't have to be correlation coefficient. It can be like any parameter you want between two columns. So more often than not, it's used for correlation coefficient. Now, correlation coefficient just means, if you remember from like middle school, right? If you draw the line of best fit, how close to like a slope of 1 can you get, right? Or like how closely correlated are those two columns, right? So obviously, trivially, column A and column A, they're perfectly correlated, right? And right, so but column A and column B are correlated. I have a 0.8 correlation, right? R squared squared of 0.8, right? Notice that this reflected on the diagonal is the exact same graph. So you're sort of like wasting half the squares. But that, I guess that's okay, right? So like notice this box is the same as this box, this box is the same as this box. This is C and A, and this is also A and C, but sort of R squared values are commutative, which just means like AC equals AE, right? Right, and again, the darker the color means the greater or the more correlated those two columns are. However, I'd like to mention this is not always true. Sometimes they specify like a color bar here. And again, my graph is inverted. My color map is inverted because I like to use a dark, like night mode background, I guess. Now, the core advantage of using a heat map is that you can immediately tell which columns are correlated with other columns. And this you'll learn later in linear regression, maybe, that this is extremely important, and which columns are correlated to another, right? Because the correlation sort of allows you to predict, and the more correlated it is, the better your prediction will be, right? And if you ever learn linear regression, if you ever want to pursue a field in data science, one thing you'll very often be doing is combining like 20 different columns, seeing how you can like add different weights to them to try to predict the 21st column, right? And that's called like linear regression, and how accurate you are, etc. That's called like a linear regression model, right? But the very first step is this heat map, right? Notice that these are your number of columns, right? So if you're working with a table with like 300 columns, your heat map is not going to be legible, right? Because you have way too many columns. You can overplot in columns as well, right? So, and normally you'll want to pick out the columns that you think will be correlated or will have useful information, right? And as always, it's always very easy to plot, right? Seaborn heat map, you don't even have to, there's no X and Y columns because you're using all the columns in the data frame, right? So you just heat map and put your data frame and you're done, right? So now I want to take some time to talk about common graphing mistakes. This is actually something I wish I learned in like the high school days. I learned this like way too late in my life, I guess. These like very common graphing mistakes. So I've already talked about a few, right? The very first one was using like a bar plot to plot continuous variables, right? So you get like overplotting in the x-axis. And the second one is overplotting, where you sort of lose the vital information or trends when you have too many points on the graph. I'll talk about a few more, right? One thing lots of news articles do, which is very scummy, but I think I saw it on Fox News once. That was like my real life, like real life incident, I guess, of this happening is it's called the y-axis manipulation, right? So if you notice, look at this graph. This blue bar looks like it's like maybe like 2.5 taller, 2.5 times taller than this graph here, right? And so you look at this like, oh wow, there's a lot more incidents after this X event, right? Right, but in reality, they simply just cut off the y-axis, right? So what looks like a triple in increase is actually only 3 more, right? So this is a 42, this is 45. That's like what, like 7% increase, right? That's not a lot, right? As opposed to like a 300% increase is what this graph is trying to show you, right? So you can do like all this sort of like this y-axis manipulation, and again, this is like very scummy. You're trying to like mislead the audience, right? Which is not what you want to do when you want to graph, right? You want to be as obvious as possible, right? Another thing people do is what's called abusing lengths, right? So this normally happens when instead of using like well, I guess this graph shows it perfectly, right? So they're trying to compare two different categorical variables, right? But instead of just using, I guess, a table, they want to graph it in a way that's, I guess, visually appealing, right? Where they just have, if you have USA, you're like this length block, right? If you're Japan, you're like this length. So the Subaru's from Japan, the Mustang is from the US, right? So the Accord is from where? Japan. The Le Car, probably from France. Yeah, okay, from France, right? But this is called abusing lengths, right? Because notice how these cars from like Sweden look quote unquote longer than the cars from Japan, right? So the Saab 900 looks quote unquote longer than the Subaru, right? It sort of gives an impression that there's more of some value, or like more Saabs than Subarus in the world, for example, right? But of course, I'm pretty sure that's not true, right? And it's only because they made this x-axis like this. They sort of like ordered it in a very awkward way, right? Because they're sort of trying to graph comparing two quantitative variables, right? And this is again very misleading, right? Because you're sort of abusing this notion of length, right? And the notion of length is giving a very confusing outcome. And this actually happens more often than not. So be on the lookout for this. And obviously do not graph anything like this, right? So another very common thing I've noticed, or not noticed, but like another very common graphing mistake is called jiggling the baseline. So in this graph, right? Let me ask you a very simple question, right? So like which one of these columns or which one of these X values has the most amount of light blue in it, right? Now this becomes very obvious, right? You look at these light blues, okay, right here, 7, right? It's definitely got the most value, or like most density, right? It's got the most light blue out of all these other columns, right? But if I ask you which X value has the largest amount of orange, right? Which this orange could just be like another category, right? Which one has the most amount of orange? You sort of have no idea. It's sort of very hard to tell, right? Like between these two, it's already very hard to tell. I mean, I guess this one looks shorter, but like the reason why it's so hard to tell is because your baseline has moved, right? So in this case, in the previous example, or the light blues, right, your baseline is the ground, right? It's always the same baseline, and that's should always be the case for bar plots, right? However, if you do stack the bar plot, if you try to stack bar plots like this, more often than not, what will happen is that the baseline for a color, for example, will be completely disorientated. So like, for example, the orange, the baseline is sort of this like hill, right? And you sort of have no idea how to compare these oranges anymore, right, with each other, because the baseline has shifted, right? So hence the name jiggling the baseline. So it's sort of, that's why like stacked bar plots are also looked down upon because of this like jiggling the baseline thing. But yeah, just know that like be cautious about this, right? So like although this graph looks very visually nice, these oranges are like sort of not comparable. And maybe in this certain case that's not important, but just know that if it is important, we sort of can't tell, right, visually or obvious. And as mentioned before, our graphs should be as obvious as possible. And lastly, I want to mention that area charts are really bad, right? Because they're very, very easy to misinterpret, right? So the classical example is a square, right? Because if you double the length of a square, right, you actually quadruple the area, right? So that's like sort of not represented, right? So if you want to use area to represent a statistic, right? So for example, this box represents 284.4 billion, right? This box, which is quote unquote half the size, right? Because the number is half the size, the number is half, right? Should should be like sort of have the size of the box, right? But from a direct look at it, it's not so obvious, right? Because of how sort of like the nature of area, right? It's not very obvious that the area of this box is half the area of this box, right? So at a quick glance, you'll think this looks maybe like 3/4 or something, right? But that's like very confusing to the eye, and that's why area charts are pretty much never used. You can think of it as like ordering like the difference between like a medium and a large pizza, right? Where like the large pizza sort of doesn't feel like it has much difference, but in reality, it's actually like a lot more pizza, right? Because of how area works, right? So if I were to plot this instead as a nice line plot, notice how it's so much more obvious what's going on, right? Than this area plot, right? Like, so for example, if I told you like this Egypt square, right? And I ask you how many times bigger is this square compared to like Kenya, it's not very obvious, right? But if I look at Egypt here, look at Kenya here, okay, that's so obvious, right? Now, pie charts are sort of also very non-obvious, which is why we normally never use them. We always stick with bar plots because they're a lot more obvious, right? So for example, here, what is the percentage area of this orange, right? It looks maybe like anywhere from like 35 to 45%, right? At 10% is already very large, right? So like, it's very hard to tell, right? What about this like green area, right? It's very hard to tell. Okay, so that's why we basically never use pie charts. I'm not even sure if you can even plot a pie chart in Seaborn, because of how useless they are. But yeah, just know that you basically never use a pie chart, just always use a bar chart instead of a pie chart, because it's a lot more obvious, right? You'll see the heights and be able to instantly compare which one is which, which one is more, which one is less. Oh, I see. Okay, so lastly, oh, wow, I actually went through my slides a little quickly today, but that's okay. Lastly, I want to talk about graphing transformations. So first of all, why do we even need to transform our data in the first place, right? Why not just graph as is, right? And you'll soon learn later on, and I guess in linear regression, for example, right? We always want our data to have linear relationships when making predictions, right? So what this allows us to do is easily define the relationship between the x and the y. I shouldn't say axis, I should say column, or I guess axis, because column doesn't make sense. But the columns are plotted. You can easily define the relationship between those two columns, and you can make the line at best fit, quote unquote, useful, right? So if we, okay, so if we look at this graph, for example, what is the relationship between the gross national income per capita and the adult literacy rate? Okay, you look at this, it's very not obvious what the relationship is, right? Right? Because of this like very funky shape, right? However, if you do a log transform, right, then suddenly it becomes very obvious, right? It becomes this like very nice, oh, this is this log transform and this is the fourth path, right? You get this very nice linear line, right? And suddenly it's a lot easier to sort of guess or like predict where you are, right? Because this graph is sort of like unlegible, right? It's not obvious, and we do not like that, right? So again, and now the question arises like, okay, so how do I turn this into this nicely transformed graph, right? Keep in mind, transformations, all we're doing is taking the log of the x-axis and taking or like squaring the x-axis or like square rooting it, right? And like doing things to the y-axis, similar things to the y-axis. We're not changing the data itself, right? We're only changing like, what will happen is like if we take the log of a really large number compared to like a medium large number, the larger number will sort of shrink a lot more than the medium large number. If that makes sense, That's just like sort of the principle, like the idea of logarithms, right? Like similarly, if you square a larger number, it will blow up a lot more than if you square a smaller number, right? It's like 5 squared is 25, but 10 squared is 100, right? So that's like 4 times more, even though 10 is only 2 times more than 5, right? So that's sort of the idea. So the question arises like, okay, how do I transform? And that's actually very obvious. Because of what's called the Turkey and Mosteller bulge diagram, right? So it's a very lengthy name. I normally just say bulge diagram, but I guess that has certain connotations. But how you interpret this graph is that if my graph is curved in one of these 4 directions, I can choose any of these 4 operations to sort of fit it into a linear shape, right? So for example, in our previous example, our graph is definitely curved this way, right? Like this way, like right. So like this here. So we have like 4 different options. We can either log the x-axis, square root the x-axis, square the y-axis, or cube the y-axis. Right, so in this case, we did both. I guess 4th power. So we wanted like a more extreme version. We took the y-axis to the 4th power, and we took the log of the x-axis, right, to get this nice linear looking graph. So, and that's just it, right? That's all you need to know how to transform. And yeah, that's actually today for this lecture. Next week, we'll be talking about, we're going back to data frames. I sort of skipped merging when we were talking about because I wanted sort of to jump straight into like graphing. But merging is like another big topic when it comes to tables. It's like similar. Okay, maybe it's not as important as say group by, but it's very important because in the real world, obviously, the table is not going to all come into one table, right? You're not going to get like one table of all data you want. You're going to have to like merge different sources together. That's what merging is useful. And I was also thinking about teaching you how to do how to make interactive plots, which just basically means like you can hover over a point and it'll tell you like things. But I also forgot how to do that, so I'm gonna have to relearn that if I'm gonna teach that. So like a quick recap of today. If you want to plot 2 quantitative variables or a relation between variables, use scatter plots. I'm sure you've learned about like the different metrics you can use in a scatter plot. If you have too many points, for example here, you can use jittering. If that does not solve it, you can use a hex plot. But if you have, for example, more than one hue, right, you can use a contour plot, right? If you, for example, are feeling fancy and you want like 3 plots in 1, right, you can use a joint plot. The heat map is used basically before you even do any analysis. This is like sort of the first analysis you do to detect correlation between different columns. Some common graphing mistakes is don't manipulate your y-axis. If you take the log of it, be sure to be very obvious that you logged it, right? Or squared it, right? Make sure to like label it, right? That's why labels aren't so important, right? Don't do this, like whatever this is, okay? If there's an order, don't make an order. Try not to jiggle the baseline. Sometimes it's fine because it's like not as important. Like maybe it's like bottom values are more important, but try not to jiggle. Maybe just try not to use the stacked bar plots. I mean, I guess they look kind of visually appealing, but they don't give off obvious information. Just don't use area charts at all. Don't use the pie chart either. And transforming data is very easy. Right? That's pretty much all you need to know. And if you ever see something sort of ugly like this, you can make it into something pretty like that. And yeah, that's it for this week.